Alright, good morning. Welcome to lecture number 21 in our course on silicon and wide bandgap power devices. Again, I am Anant Agarwal with the Department of Electrical and Computer Engineering at the Ohio State University, and with me is Dr. Arash Salami in my group, who has been very helpful in putting these lectures together. So, today we are going to cover several topics on silicon carbide power MOSFETs. So far we have covered the basic MOS characteristics, the fact that inversion layer mobility is low, and then we have gone through a planar DMOSFET structure. And we have talked about the breakdown voltage of the planar DMOSFET structure for punch through mode and non punch through mode. And then we have talked about how to reduce the gate oxide field by moving the P wells together or controlling the doping and the width of the JFET region. So, today we will talk about the calculation of the specific on resistance when the MOSFET is on, and then we will get into some 2D device simulation results. So, let us start with the specific on resistance. So, here is a cartoon of simple planar silicon carbide DMOSFET, and we are only showing half the cell. The other half of the cell would be a mirror image of this cell reflected on the right hand side. So, again, looking at this simple half cell, we have the gate oxide, we have the P-type silicon carbide here, which forms the inversion channel. We have source and body contacts, and we have a high dope P plus shielding region. And the purpose of that we will discuss in a later lecture. But this is where the inversion channel is formed at the surface, and the electrons can flow from source to drain. We have also labeled some critical dimensions, such as Tp here is the thickness of the P well plus P plus shielding region. T is the thickness of the drift layer. S is the width of the P well, and WP is the depletion region on the JFET side because of this PN junction here. And basically we will consider the depletion WP on the N side right here at this point, and as you will see that then determines the JFET resistance. And WJ is considered to be the width of the JFET region, and L channel is the length of the inversion layer channel, and half pitch of the cell is P. So, the real cell with the complete mirror image of this cell would have a pitch of 2P. All right. So, when we turn this device on, so let us go back and look at it. We apply positive gate voltage and we turn the device on, meaning we form the inversion channel here shown by this. Then the electrons flow from source through the inversion channel down the JFET region through the N minus drift region, and here the current spreads at a 45 degrees angle, and then the current flows vertically here at the end of the cell, and then we have the N plus substrate. So, there are various sources of resistance in the on state. First is the channel resistance, and we will find that this is the dominant resistance in silicon carbide DMOSFET, because our inversion layer mobility is very low. Then we have a accumulation resistance, because this layer here will be accumulated of electrons. So, we will have more electrons here, and that accumulation resistance we will neglect, because most of the electrons will come and flow through the JFET region very close to this boundary. So, in other words, they will not go further up and go down, they will mostly hug this boundary here. Then of course, the JFET resistance, which is the resistance of the JFET region, and then the drain resistance, which is the resistance due to spreading of the electrons, and then the parallel region here, and then the substrate resistance. So, in addition, we have two more resistances that we will talk about when we solve a numerical problem later on. One is the contact resistance between the source and N plus. So, there is a contact resistance, and then there is a resistance of the N plus source that we will calculate also. So, let us start with the channel resistance. We had shown you that in the linear region of the MOSFET, the channel resistance is simply inversely proportional to the inversion layer mobility and oxide capacitance, and of course, Vg minus Vt, where Vt is the threshold voltage. L channel is the effective channel length, and P is the half pitch of this cell. So, the reason that pitch P is there is because we are trying to define the specific on resistance. So, everything is normalized to the area of this cell looking from top down, and we can consider the width of this cell in the z direction into the plane of the paper as 1 over p. So, if p is the pitch this way and the width is 1 over p, then the cross sectional area looking down upon it would be simply p times 1 over p, which is 1. So, specific on resistance means the on resistance applicable to 1 centimeter square device. So, that is why this pitch appears here in this equation. Then accumulation layer resistance is simply defined by this accumulation layer, which is same as the channel resistance, except channel length is replaced by the width of the JFET region, and we put a fudge factor k because of the 2D nature of this region. So, the electrons, according to this, what we are calculating is this resistance, but by putting a k which is less than 1, we account for current spreading into JFET. So, more current flows near this edge than and less current flows near the center of the JFET region. So, k could be, depending upon the geometry, could be anywhere between 0.1 to 0.6. In our example, we will essentially neglect this resistance, but some small numbers present, and we should just be mindful of that. Then the third component is the JFET resistance, which depends on the resistivity of the JFET region times the thickness Tp times the cross sectional area, which is proportional to the width of the JFET region minus the little area which is depleted here, Wp, right. So, we are only concentrating on this cross sectional area, which is Wj minus Wp, and again the pitch is there because we want to normalize it to the chip area of 1 centimeter square. From earlier discussions, you can calculate the depletion with Wp on the JFET side by looking at the built-in potential, which is simply 3.3 volt approximately for silicon carbide, and the doping in the JFET region. Then comes the drift layer resistance, and drift layer resistance is essentially the resistance of this layer which is spreading. That means the cross sectional area of this drift layer resistance is constantly increasing as we go down. So, we really have to integrate to get the resistance of this spreading region, and I have done the integration for you. You can verify that that resistance is the resistivity of the drift layer times pitch times the natural log of P over Wj minus Wp. Wj minus Wp is essentially this width of this cell, and then for the parallel part where the current is flowing vertically, because now it merges from the electrons coming from the other cell, is that resistance for this little piece here is simply the resistivity times T minus S minus Wp, which is basically the length of this region. But I would encourage you to do this integration so you can verify the resistance of the spreading region. And then the substrate resistance is simply the substrate resistivity times the thickness of the substrate. There is no pitch P here because this substrate is over the whole cell, so we don't have to normalize anything with respect to the pitch. All right, so these are the various components. Then let's go ahead and look at an example, numerical example. So we take a sample designed for 1200 volt silicon carbide MOSFET, and we give you some of these numbers for different dimensions and different dopings and different thicknesses, and I would encourage you to stop the presentation here and understand what these numbers are with respect to various equations. And then we will go ahead in the next few slides calculate different components of this resistance. So the first one, obviously we will calculate the contact resistance of the source. So here we have shown you a 3D cartoon of the MOSFET. Again, different dimensions have been labeled, and we have taken the Z direction, which is into the plane of the paper. The width of that device in the Z direction is 1 over P. So the cross sectional area looking down from the top is P times 1 over P, which is 1 centimeter square. So all the resistances we now calculate will automatically be specific on resistances, meaning resistance of the 1 centimeter square device. So, the half pitch of this cell P is 5 microns, as you can see from the picture, and various dimensions that have been given to us, and 1 over P is simply this number here in centimeters, and again the total on resistance is the channel resistance plus the accumulation layer resistance, which we will neglect, JFET resistance, DriftLayer resistance, substrate resistance, plus we have added the contact resistance of the drain side. This is the contact resistance of the drain side. We have also added the contact resistance of the source side and the resistance of the source, which is indicated by this green resistor. So, let us go ahead and calculate these different components, and again I would encourage you to stop this presentation and make sure you understand the calculations. The first one we calculated the source contact resistance. So, the source contact resistance to us is given as 10 to the minus 6 ohm centimeter square. So, if we simply divide it by this area, then we will get the then we will get the source contact resistance in absolute numbers. So, we have gone ahead and divided by this area, which is 1 micron times 1 over P, and what we get is a number of 5 micro ohms. Now, which is nothing but 5 times 10 to the minus 3 milliohms, and now we have added centimeter square to it to indicate that the cross sectional area of this entire cell is 1 centimeter square, and whatever resistance we have calculated in absolute ohms for this source contact resistance is actually the specific on resistance, which is milliohm centimeter square. Now, same thing, we do the source contact resistance, which is essentially the resistance here of the N plus region. You can see the length L is 1 micron, the depth of this source is 0.5 micron, the doping is 2 times 10 to the 19, and mobility of electrons is given for that doping to be about 80 centimeter square per volt second. So, now we can calculate the cross sectional area for the electrons to flow from left to right along the source, and that would be 1 over P times the thickness of the source, and that comes out to be 0.1 centimeter square. And then we can calculate the source resistance by a simple formula given for the resistance, thickness divided by cross sectional area times the resistivity, which is 1 over Q times the mobility times the doping. And you plug in all these numbers, you get an absolute resistance of 3.9 micro ohms. And again we have added centimeter square to this number, so that now 3.9 times 10 to the minus 3 milliohm centimeter square reflects the specific on resistance of the source. So far you can see these numbers are very small, but they are finite to begin with. So, that tells us that we need to achieve very good contact resistance of 10 to the minus 6 ohm centimeter square. That means the N plus doping has to be high, so we can get really low contact resistance, and also the doping of the source has to be high, not only to reduce the contact resistance, but also to reduce the lateral resistance of the source. Then we can go ahead and calculate the channel resistance for the given oxide thickness of 50 nanometers, which is simply 500 angstroms. We can calculate the oxide capacitance, assuming the electric constant of oxide is 3.39 and permittivity of free space is 8.85 and minus 14 farads per centimeter. Oxide thickness is 50 nanometers, which is 500 angstroms, and we have represented that in centimeters. So you can get the oxide capacitance per unit area, and then we can go ahead and plug in the numbers for half micron channel length, pitch of half pitch of 5 microns, inversion layer mobility of 10. So please notice that we have assumed a very low inversion layer mobility. This has been a problem for silicon carbide. In silicon, that number would be of the order of 300 to 500. So, and then we have plugged in the oxide capacitance and 20 volts for the gate voltage minus 2 volt for the threshold. We get 2 milliohm centimeter square as the channel resistance. We have neglected the accumulation layer resistance, and then for JFET resistance we have calculated the WP, which is depletion on the JFET side, and that comes out to be about 0.34 micron. So remember, the JFET is 1.5 micron, so 0.34 micron is a substantial portion of that is depleted. Doping of the JFET region is 3 times 10 to the 16, and we have calculated for that given doping what would be the mobility of the electrons in the JFET region, using this expression which we had given you earlier many lectures ago, that basically gives you doping and temperature dependent electron mobility for n-type silicon carbide. So now we can go ahead and calculate the resistivity of the JFET resistance and then plug it into the expression for our JFET, and we come up with 0.08 milliohm centimeter square. So you can see, since we doped the JFET area with a higher doping than the DriftLayer resistance, my JFET resistance is very, very small. Supposing we had not done that, then our, let's say the doping of the JFET was the same as our DriftLayer resistance and our DriftLayer doping, and our DriftLayer doping was let's see, our DriftLayer doping was given as 1 times 10 to the 16. So if we reduce this to 1 times 10 to the 16, then the DriftLayer, the JFET resistance will go up by a factor of 3, and now it will become somewhat like 10% of the channel resistance. So right now it's very small, and that's because we have doped the JFET region with much higher doping. Then we can go ahead and calculate the DriftLayer resistance. Again, we have calculated the DriftLayer mobility by using that expression corresponding to this DriftLayer doping, and plugging in these numbers, we get the resistivity of the drift layer, and then we can calculate the spreading and the parallel plate part of the JFET of the drift layer resistance as 0.855 milliohm centimeter square. Again, you can see this is a much smaller number, which is why we use silicon carbide, because for a given breakdown voltage, we can dope the silicon carbide drift layer much higher and make the thickness smaller. So both of these factors reduce the drift layer resistance to a very low number, and this is why we want to use silicon carbide as opposed to silicon. Substrate resistance, substrate resistivity is typically 0.002 ohm centimeter. Substrate thickness is typically 400 microns. So you multiply the two, you get 0.08 milliohm centimeter for the substrate resistance. Drain contact resistance is typically, assuming contact resistance is 1 micro ohm centimeter, we basically multiply by the backside area divided by the backside area of the cell, we get 1 times 10 to the minus 3 milliohm centimeter. So we have now calculated all the components so far, and now you can see the total resistance, which is the sum of all the components, is 3.028 milliohm centimeter square for this device. And this table shows you absolute and percentage contributions from each resistance, and you can see the highest resistance comes from the channel. So this is because our inversion layer mobility was very low. We assumed it to be 10 centimeter square per volt second. In silicon, that number is 300 to 500. So in silicon, that number would not be dominant, but in silicon carbide, channel resistance is the dominant factor, and that's why we try to reduce the channel length and reduce the oxide thickness to reduce the channel resistance. And then you can see the second biggest number is the drift layer resistance, which is only about 28%, and the rest of the numbers are relatively small. Then thinking about silicon, in silicon you will find that the drift layer resistance is the dominant because the breakdown field is lower. That means the drift layer thickness would be thicker and lighter doped, and the channel resistance would be much smaller because the channel mobility of electrons in silicon, as I said, is between 300 to 500. So here we have different components, and as you can see, the biggest contribution in silicon carbide comes from the channel resistance, and then the next one is the drift layer resistance. So it's very interesting to see this, and from this we can conclude that we have to spend maximum effort on reducing the channel resistance for a given voltage. Obviously, as we go to higher and higher voltage devices, the drift layer resistance will go up, channel resistance will remain the same. So the percentage contribution of the channel resistance will reduce and the drift layer resistance will increase. So for very high voltage devices, 6.5 kV or 10 kV, this channel resistance is not a limitation because the drift layer resistance tends to dominate. This being a 1200 volt device, roughly 66% of the resistance comes from the channel. All right, so now let's get into the next section, which is design and simulation of 1.7 kV 4H silicon carbide planar DMOSFET. So, we want to design a 1.7 kV D MOSFET. So, let us start there. So, here is the full cell of the silicon carbide D MOSFET, one such cell, and the MOSFET will consist of thousands of these cells put together, right. So, we are only showing you one cell with a total pitch of p micron. So, in the previous example, we were only showing you half the cell with a half cell of pitch p. Here we are showing you a full cell with a pitch p. It really is not important, but we have chosen some dimensions here for different parts of the MOSFET, which you can see. We can also look at the doping numbers. P well doping at the bottom is 10 to the 18. At the surface is about 2E17. We have taken the JFET region doping to be 3E16, and you can see channel length of 0.5 micron. Inversion layer mobility in the channel is 10 centimeters square per second. And in order to calculate the drift layer doping and thickness, we have used our expressions for the optimum punch through design, and from that we get a drift layer doping of 5.2 times 10 to the 15 and thickness of 16 micron. Critical field for now we have assumed to be 2 megavolt per centimeter, but please remember that is a function of the doping of the drift layer. And the breakdown voltage is about 1870 volts. So, we always add 10% margin to our 1700 volt to make it 1870. So, we plug these numbers in, we get 14 micron of thickness. For conservative design, we have increased that 14 micron to 16 micron. And this is the first simulation. So, what we are going to do is try to decide what is the optimum JFET width of this cell. The optimum JFET width of this cell, we will vary from 1 to 4 micron, and the reason we are varying it is because we want to minimize the field in the silicon carbide and field in the gate oxide, so that this device has good long term reliability, which means we will try to keep the gate oxide field in the blocking state to about 4 megavolt per centimeter, and that will depend on what is the width of the JFET region. So, here is the first simulation. We have taken half JFET width to be 2 micron, meaning 4 micron total JFET width, and we are looking at the electric field along this red line in the middle of the JFET region. When we have applied a full voltage, in this case of about 1700 volt, and we see actually 1800 volts is what we have applied. So, you can see as we go from 300 volt in steps of 300 volts to 1800 volt, we come up with this orange curve. So, this looks like a trapezoidal field. Here it punches through our 16 micron of epi layer, and this is where we are in the substrate, but near the JFET region you can see the electric field starts going down and then goes back up in the oxide. So, here is the oxide electric field right here, which is about 4.6 megavolt per centimeter. In the JFET region, the field is between here to here, but remember the field in the gate oxide is multiplied by the ratio of dielectric constants, which is about 2.7. So obviously this gate oxide field is very high, so we are going to reduce the JFET region to see what happens. So here is the half JFET width of 1 micron, and you can see even before we approach the JFET region, the electric field starts reducing, and then it reduces through the JFET region, and the oxide field is little more than 3 megavolt per centimeter. So this looks like a good design, but let's go ahead and see what happens when we reduce the JFET, half JFET width to 0.75 micron. So now you can see more dramatic reduction in the electric field, and also the electric field in the oxide is reduced to below 2.5 megavolt per centimeter. So this is a very safe design, but you can see as we are bringing the JFET region smaller and smaller, the resistance of that JFET region will go up, as you just saw in those calculations. So we have to be mindful of that. Here is a more dramatic reduction in the surface field if we make the half JFET width to be about half a micron, and you can see that the electric field in the oxide is 1.4 megavolt per centimeter. But obviously the resistance in the JFET region is going to increase. So in the next slide, we will plot the peak oxide field in the semiconductor. We will plot the surface, we will plot the oxide field here, and we will plot the perhaps this field in silicon carbide, the surface field. So here we go. We have plotted the surface electric field in silicon carbide, and this blue line is actually this number here. Then we have calculated the peak electric field in the drift layer, and that's this number here. And then we have calculated the oxide field, and that's the number indicated by this number here at 1800 volts. And you can see that as the surface oxide field in silicon carbide increases, the oxide field also increases by the ratio of 2.7, and the peak electric field doesn't change much. So we just have to keep our eyes on this oxide electric field. Then what we have done is also calculated the output current characteristics for 20 volts on the gate with different JFET gaps, and you can see as we reduce the JFET gap, the resistance goes up because the width of the JFET is reducing. So now we can, by reducing the JFET width, we can reduce the oxide field, but the JFET resistance goes up. So we are plotting both of these numbers here on this chart. So what we have done is plotting the specific on resistance of this device as a function of half JFET width. So what we have done is taken the slope of these on output curves and converted them to specific on resistance by multiplying the cross sectional area of the cell, which is different for different JFET widths, right. So basically let's go back. This is the area looking down from the top, and that pitch is going to change as we change the JFET gap. So, we have calculated the specific on resistance here and plotted it, and you can see as we increase the JFET width, the on resistance goes down, but the electric field in the oxide goes up quite a bit. So, we want to keep the oxide electric field to about 3 megavolt per centimeter, and we can see just eyeballing this, if we select this point, which is half JFET width of 1 micron, oxide field is only 3.1 megavolt per centimeter, and specific on resistance is about 9.3 milliohm centimeter square. So, this looks like a happy medium. We want to minimize the on resistance and we want to minimize the electric field in the oxide. So, what we have done is we have multiplied the electric field in the oxide times the specific on resistance and plotted it as a function of JFET, half JFET width, and you can see that the minimum occurs at half JFET width of 0.5 micron. And we could choose anything to the right or the left, but we are hesitant to select anything to the left because this resistance will rapidly keep on going up as we reduce the JFET gap. So, this curve will quickly rise. So, to be on the safe side, we can choose half JFET width of 1 micron. So, even if there is some error or some design bias or process bias, so that exact JFET width is different from 1 micron, we will still be close to this minimum value. So, this looks like a good design point of half JFET width of 1 micron. If it becomes 1.25 micron, we are here. If it becomes 0.75 micron, then we are here. We are close to, we are not going to drift too much away by process or design bias. So, that is a good design point of 1 micron half JFET width, and which means the total JFET width is 2 micron. So, this is the cell now. Channel length is now the next thing we need to decide is what is the channel length, and that depends on the output characteristics of this device. I think we should stop here. Today we have optimized the JFET width based on different considerations between the on state resistance and the maximum oxide field in the blocking or off state. So, next time we will continue this discussion of this simulation and try to get a handle on the channel length. So, thank you very much and we will see you next time.